EET 118 Lab AC5 frequency response of RL and C components. I'm going to show you how to do this circuit real quick. This is part one. So we have a AC voltage source here, amp meter, and then a 1K resistor, and we're monitoring the voltage across it, and we're looking for 4 volts peak to peak. So if I go over to every circuit, I started a new circuit, and I'm going to put in an AC source real quick, put in a resistor, put in an amp meter, put in a voltmeter across this thing, and then connect them up. So here I have my circuit built, and I'm going to play it, and you can see it's right now it's 1 volt peak to peak. I'm looking at see the when you click on these two, you can see the difference. This is the voltage across the resistor. This is the current flowing through. So the goal was here to get this at 4 volts peak to peak. Right now it's only 2 volts peak to peak. It's an amplitude of 1. So I got to take this, change the voltage, turn it up to 2. It was set to 1. And now it's 4 volts peak to peak. You can see the min and the max is 2 volts. So now we have everything set. And then what we want to do is look for, record our voltages or record our current. So if we go back to the table, what it did was we're changing frequencies, and then the voltage across the resistor set to 4. Then you do the calculation. You take the peak to peak voltage divided by 2, and then you divide it by the square root of 2 to get the RMS value, or multiply by 0.707. So that's 4 divided by 2 is 2, divided by the square root of 2 is, again, the square root of 2, which is 1.414. So then what they want you to do is write down the currents that you're going to measure. So if we change this to 50 hertz, what measurement do I get for my current in RMS value? So I go back to the circuit, and I'm going to change this to 50 hertz. Right now it's set to 1K. So I'm going to change it to 50, and then see what I get for my current. See how it's taking a little while to adjust. So it's going to go back and forth, and um, it's going down, down, because it has to change to that value, so it takes a little time. Big difference between 1 kilohertz and 50 hertz. So it's getting down into the milliamp range, and it looks like it's going to bottom out pretty soon. I'm going to turn this off just to make it easier to see. So, because we aren't worried about the voltage now. Oh, this is messed up. This doesn't help me at all. So it looks like it's it's topping out at 2 milliamps and probably minus 2 milliamps. Now, I think we need to change our time here. Yeah, this is a good tool. So you can see now we're at a more proper time scale. I made a 3 3 milliseconds per second of division. So now you can see that it's going between plus and minus 2 milliamps. So going back to our table, I put a table into Excel. So it was 2 the peak current was 2 milliamps. So I want to divide that by the square root of 2. So I'm going to take that, and that means 2 to the half power, which is the square root. So forgot you got to put an equals in front of it. So there it is. It's 1.414 milliamps, and then if you go down the list, there it is. It populated everything. So this is my table: frequency in hertz, uh, resistor in volts, the voltage across it. Then this RMS voltage, it's this value divided by 2, and then that value divided by the square root of 2. And then I put in 2 here. So I only did 50 hertz though. Let's go back and check it out for 100 hertz. So we're going to change this to 100 hertz. Play it again. And you can see it's still the same current. So then I'm going to change this again to, what was the next value? 200 hertz. That's the same current. So I'm going to go to 500 hertz. Same current. I'm going to go to 1000 hertz. Same current. So we might want to change our time here a little bit to make more sense. So anyways, you can see that that's the point of this lab, is you can see that frequency has no bearing. It just doesn't change the current for the resistor. So that's what I would expect for the first table. For the second table, we're looking at a resistor in series with an inductor. And again, we're looking for 4 volts peak to peak across the inductor. We have a voltage source here. So it's a little bit trickier, but not really. So if we go to this part 2 here, you see that I have it built. I have a 100 ohm resistor here, ammeter, voltmeter, a 10 millihenry inductor, and I have a AC voltage source. So the goal was to get 4 volts peak to peak across this, and I believe that I've done that. Yeah, so you can see it's 2 volts peak to peak. I had to tweak this, okay, to get this to work. Obviously, you go in here. This is what I had it set to. But again, it was like a trial and error thing until I got that, just like you would do in the lab. So this is what I expect. We could go further with this, but it's very similar. The other, parts 2 and 3 are similar to this. Part 3 is, well, I actually did part 4. I put a part 3 is just with this capacitor, but then part 4, or the last exercise, you have to add this capacitor in front of it. So if we go back to part 2, like for a 1 kilohertz frequency, we look at the current here, and I'm going to turn this off. I think I was looking at this. I'm turning on too many things. Here we go. So right now, this is 31 milliamp plus or minus. So the peak to peak milliamps would be 63.4. Or, yeah, 63.4. Be 31.7 times 2. And the RMS value is going to be 31.7 divided by the square root of 2. So that's what you need to put in this table. And I just copied the other table. These are not the correct values in here. I was just messing around with this, but the other table is the table that's shown in here. So what you're going to do here is you set the voltage across the inductor to 4 like I showed you, and then you set these different frequencies, and then you're going to take the peak to peak voltage across the resistor, which would be, oh, it would be this voltage here. And then you calculate using this value, calculate divided by RS. Now RS is going to be perfectly 100, but in the lab it's not going to be exactly 100 in real life. So then the next step is you take this number, which is going to be 4, and you divide it by this number that you calculated, and that's going to be your inductive reactance. And then you take just a pure calculation of 2 pi FL. Now L is going to be 10 millihenry, so um, depending on the frequency, it's going to change X of L. And then you just go through the lab and same thing. You're going to do a plot. So I expect you to do a plot in Excel, frequency versus XL, and then do some calculations here. Then the same thing here. You put a capacitor in series with an inductor like the other part I showed you. Then you do the same kind of calculations. Then you do the same plot. Answer all the questions. Now, in the answer sheet I put on there, every one of these boxes you have to put in a value for, and I think I put them in the column form. So I went down the line, I just changed the frequency, and I said what's VRS peak to peak for each frequency, and then I went to I peak to peak to peak, and then XC measured all these values, and then XC calculated all these values. Probably what you're going to end up getting is like these numbers are going to be very, very close. They might be identical because this is a perfect situation. It's not laboratory. Laboratory, you're going to get a slight difference between these two numbers, but it asks you about that. And then you plot XC versus F, answer these questions, and then what you're doing is part 4. You are going to I gotta save this first. You're going to add another capacitor in series with this capacitor, and then you just take the same measurements and answer more questions. And then again, this exercise, it wants to know what would happen if you made this 20 millihenry. So you can change this from 10 to 20 and find out. And then again, same thing here. It wants you to set that at 7.2 volts peak to peak, and then figure that out. But you can do all this by hand. You don't need every circuit to do this. Um, Same thing with this. You should not need every circuit to figure this out. And then this last part, you can do this in every circuit if you want to figure it out, or you could just do it in Excel from your graph. So That's about it. So hopefully that helps you get through this lab.